We're burning trillions chasing a dead planet. It's a billionaire's fantasy draining resources from the only world that can actually save us. It's all a dangerous fantasy built on wishful thinking and ignored physics. Mars isn't our future. It's a graveyard waiting to happen. And here is a question. If you could bring only one item to Mars to save your life, what would it be? I will pin the most creative answer. Let me know in the comments. Now let's begin. Mars itself is small, roughly half Earth's diameter, with only about 11% of our world's mass. If you placed Earth and Mars side by side, you could fit almost 7 Mars-sized planets inside Earth's volume. This isn't just a fun fact for trivia night. Size matters profoundly when you're trying to build a civilization. A smaller planet means weaker gravity, about 38% of Earth's pull. While this might sound convenient for lifting heavy equipment, it creates biological nightmares we'll explore later. But here's where things get truly terrifying. Mars has no global magnetic field, none. Earth's magnetic field wraps around our planet like an invisible shield, deflecting deadly solar wind and cosmic radiation. Mars lost its magnetic field roughly 4 billion years ago when its core cooled and solidified. Without this protection, the solar wind, a relentless stream of charged particles from the Sun, has spent billions of years stripping away the Martian atmosphere. And what an atmosphere it is, or rather, what it isn't. The atmospheric pressure on Mars averages about 600 pascals. Earth's sea level pressure is roughly 101,300 pascals. Do the math. Mars has less than 1% of Earth's atmospheric pressure. To put this in perspective, the pressure on Mars is equivalent to standing about 35 kilometers above Earth's surface, higher than any airplane flies, approaching the edge of space. This razor-thin atmosphere consists of 95.1% carbon dioxide with tiny amounts of nitrogen at 2.6% and argon at 1.9%. Oxygen makes up only about 0.16%. Even if you could somehow breathe in this near vacuum, you'd suffocate instantly from lack of oxygen while simultaneously experiencing decompression sickness as the gases in your blood formed bubbles. Scientists from the Mars Atmosphere and Volatile Evolution mission, affectionately called MAVEN, have confirmed something chilling. Mars continues losing its atmosphere to space right now, today, as you watch this video. Roughly 3 times 10 to the 26th power hydrogen atoms escape every single second. That number is so large it's almost meaningless to our human brains. So think of it this way. Mars is bleeding out into space, one atom at a time, and has been for billions of years. Recent research published in 2025 revealed something even more disturbing. When Mars's axial tilt increases during its orbital cycles, roughly every million years or so, atmospheric loss accelerates dramatically. During high obliquity periods, when Mars tilts about 35 degrees instead of its current 25 degrees, hydrogen escape rates increase by more than 10 times normal levels. Over Mars's entire history, this process has stripped away water equivalent to an 80-meter-deep global ocean. If you're enjoying this deep dive into Mars's hostile nature, give this video a like. Your support helps me bring you more content exploring the wonders and terrors of our universe. Now let's talk temperature. Mars is cold, brutally cold. The average temperature on Mars hovers around -63 degrees Celsius. That's -81 degrees Fahrenheit for those keeping track, but averages lie. At the equator during summer, temperatures might reach a balmy 20 degrees Celsius, about 68 Fahrenheit, for a few hours in the afternoon. Sounds almost pleasant, right? Wait for nightfall. As the thin atmosphere fails to retain any heat, temperatures plummet to -73 degrees Celsius, roughly -100 Fahrenheit. This isn't a gentle cooling, this is a thermal cliff that drops 100 degrees in hours. Your habitat would need to survive temperature swings that would shatter most materials. The seals on your airlocks would contract and expand daily, creating potential failure points. One crack, one seal failure, and you're exposed to vacuum. Head toward the poles during winter, and temperatures drop to minus 125 degrees Celsius, negative 193 Fahrenheit. At these temperatures, carbon dioxide itself freezes out of the atmosphere, forming vast seasonal ice caps. Picture this. The very air freezes solid and falls as dry ice snow. This process actually changes the planet's atmospheric pressure seasonally. When the southern polar cap freezes, it locks up about 25% of Mars's total atmospheric mass as solid carbon dioxide ice. NASA's Curiosity rover, which has been measuring atmospheric composition in Gale Crater since 2012, detected something fascinating and troubling. Over nearly 5 Martian years, that's 3 Earth years, instruments measured seasonal variations in carbon dioxide, nitrogen, and argon that lag roughly 20 to 40 degrees of solar longitude behind the pressure cycle. This tells us that atmospheric mixing happens slowly, much slower than on Earth. Trace gases don't distribute evenly. Regional variations would create pockets of different atmospheric composition, making settlement planning even more complex. But here's the strangest part. Oxygen levels fluctuate wildly and mysteriously. Curiosity's sample analysis at Mars instrument detected oxygen variations that don't match any known seasonal pattern. Sometimes oxygen increases by up to 30%, then drops again unpredictably. Scientists are genuinely puzzled. This suggests unknown chemical or biological processes we don't understand. Imagine trying to manufacture breathable air when the planet's own oxygen refuses to follow predictable rules. Let's dive deeper into the radiation nightmare that makes Mars one of the most hostile environments humans could attempt to inhabit. Remember how I mentioned Mars lacks a magnetic field? This isn't just an interesting geological fact, it's a death sentence written in invisible particles traveling at nearly the speed of light. Earth's magnetosphere extends roughly 65,000 kilometers into space on the sunward side and millions of kilometers on the night side. This invisible bubble deflects about 99% of harmful cosmic radiation and solar particles. Mars has nothing comparable. When galactic cosmic rays, those incredibly energetic particles born in supernova explosions across the galaxy, approach Mars, they slam directly into the atmosphere and surface with nothing to slow them down. NASA's Radiation Assessment Detector aboard Curiosity has been measuring surface radiation since 2012. The findings are sobering. On the Martian surface, you'd receive approximately 0.65 millisieverts per day. That might sound abstract, so let me translate. In 1 year on Mars, you'd absorb roughly 237 millisieverts of radiation. The International Space Station, protected partially by Earth's magnetosphere, even in low orbit, exposes astronauts to about half that amount annually. Current NASA career exposure limits for astronauts range from 600 to 1,200 millisieverts total, depending on age and gender, based on maintaining cancer risk below 3% above baseline. A single year on Mars would consume roughly 20 to 40% of an astronaut's entire career radiation budget. 2 years? You're approaching or exceeding safe lifetime limits. 5 years? You're in uncharted territory where cancer risk becomes not just elevated, but probable. But wait, it gets worse. Those measurements were taken with Curiosity's instruments somewhat shielded by the rover's body and equipment. An astronaut in a thin-walled habitat would face even higher exposure. During the transit to Mars itself, astronauts would receive approximately 1.3 millisieverts per day in deep space, twice the surface rate for the 7-month journey. By the time you arrived, you'd have already accumulated about 270 millisieverts before even setting foot on Martian soil. The Artemis 1 mission in November 2022 provided fresh data that validated our worst fears. Instruments aboard the Orion spacecraft and the Biosentinel CubeSat measured radiation levels from Earth to beyond lunar orbit during the exact same time period. The measurements matched computational models with chilling accuracy. From Earth to Mars, space radiation exposure isn't a theoretical problem we might solve. It's a confirmed killer we can measure precisely. Solar proton events add another layer of danger. When the Sun releases a coronal mass ejection aimed at Mars, billions of tons of plasma and energetic particles race outward at millions of kilometers per hour. On Earth, our magnetosphere deflects these storms, though they can still disrupt satellites and power grids. On Mars, there's no protection. A major solar proton event could deliver lethal radiation doses in hours. The October 2003 Halloween solar storms, had they hit unshielded astronauts on Mars, would have delivered potentially fatal doses. Recent research presented in August 2024 at NASA's Space Radiation Laboratory confirmed that galactic cosmic radiation intensity varies on an approximately 9.5 to 12-year solar cycle. During solar maximum, when the Sun's activity peaks, cosmic ray intensity drops to its lowest levels because the Sun's enhanced magnetic field deflects some particles. Paradoxically, this is also when solar proton events become most likely. During solar minimum, cosmic ray intensity reaches maximum levels. There's no safe period. You're either exposed to elevated cosmic rays or increased risk of solar storms. Pick your poison. The biological effects extend beyond cancer. High-energy particles create secondary radiation as they smash into spacecraft hulls and habitat walls, fragmenting into lighter but still dangerous particles. These secondary particles penetrate deeper into tissue, damaging DNA, destroying cells, and potentially causing central nervous system effects. Studies on mice exposed to Mars-equivalent radiation show cognitive impairment, memory problems, and behavioral changes. Imagine colonists slowly losing mental function, unable to perform complex tasks required for survival. Even worse, radiation damages the cardiovascular system. Research indicates that exposure to the types of radiation found in deep space accelerates atherosclerosis, hardening of the arteries. Heart disease could strike Mars colonists decades earlier than Earth-bound humans, creating a medical crisis millions of miles from advanced hospitals. Shielding seems like an obvious solution, right? Just build thicker walls. Unfortunately, the physics work against us. Effective radiation shielding requires mass, lots of it. Water, polyethylene, or regolith would work, but you'd need layers several meters thick to reduce radiation to Earth-like levels. A habitat buried under 5 meters of Martian soil would provide decent protection, but construction becomes monumentally difficult. Here's the cruel irony. The more shielding you add, the heavier your habitat becomes, requiring more structural support, which requires more materials, which must be launched from Earth or manufactured on Mars, which requires more equipment and energy. Every kilogram launched from Earth to Mars costs roughly $10,000 to $20,000 with current technology. A single habitat module massing 50 tons would cost $500 million to $1 billion just for launch, before considering construction, life support, or any other systems. Speaking of getting to Mars, the journey itself presents seemingly insurmountable challenges. We've already covered this topic in depth in another video on this channel about why returning from Mars is harder than getting there. The physics of orbital mechanics, the fuel requirements, and the complexity of Earth return create a cascade of engineering problems that make round-trip Mars missions almost prohibitively difficult. I'll put it in the description and on the card above, but let's assume that we somehow solve the radiation problem. Maybe we develop better shielding materials or pharmaceutical countermeasures that repair radiation damage, or we simply accept higher cancer risks as the price of exploration. We still face another fundamental barrier: water. Water on Mars exists, but mostly in forms almost useless for sustaining a city. The polar ice caps contain significant frozen water mixed with carbon dioxide ice. NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express have mapped extensive subsurface ice deposits, particularly at high latitudes. Measurements suggest enough water ice to cover the entire planet in liquid water, roughly 80 meters deep if melted. Sounds abundant, right? Here's the problem. It's frozen solid in a near vacuum at temperatures where carbon dioxide turns to ice. Extracting it requires enormous energy to drill through rock-hard permafrost, heat the ice to liquid state, and purify it for human use. Every liter of water would cost precious energy in an environment where energy itself is desperately scarce. Mars receives, as I mentioned earlier, only about 43% of the solar energy that reaches Earth. Solar panels on Mars would generate less than half the power of identical panels on Earth, and that's under optimal conditions. Dust storms, which can envelope the entire planet for months, would reduce solar power to nearly zero. The Opportunity rover survived on Mars for 15 years, but finally died during the global dust storm of 2018, when its solar panels couldn't generate enough power to keep systems alive. Nuclear power seems like the obvious alternative, but current radioisotope thermoelectric generators like those powering Curiosity and Perseverance produce only about 110 watts continuously. That's barely enough to power a laptop. A Mars city would need megawatts, millions of watts, requiring nuclear fission reactors with uranium or plutonium fuel. Launching radioactive materials from Earth raises safety concerns and regulatory nightmares. Mining and refining nuclear fuel on Mars would require extensive infrastructure we'd need to build first, creating a chicken and egg problem. Recent studies from 2025 examining carbonate formation in Gale Crater suggest that ancient Mars had episodes of liquid surface water that sequestered atmospheric carbon dioxide as carbonate minerals. This created a negative feedback loop. Increasing solar luminosity promoted liquid water stability, which formed carbonates, which removed atmospheric carbon dioxide, which reduced greenhouse warming, which eliminated liquid water. Mars essentially self-regulated into a frozen desert billions of years ago. This historical pattern terrifies scientists because it suggests Mars has natural tendencies toward losing atmospheric gases and water. Any attempt at terraforming, making Mars Earth-like, would fight against planetary-scale processes that have been operating for 4 billion years. We wouldn't be gardening Mars, we'd be fighting a cosmic battle against thermodynamics itself. Now let's talk about something that might seem trivial compared to radiation and water scarcity, but could actually prove just as deadly: dust. Martian dust isn't like Earth dust. It's not the fluffy stuff that accumulates on your bookshelf. Martian dust particles are tiny, averaging about 3 micrometers in diameter, and incredibly abrasive. They're made of oxidized iron minerals, silicates, and perchlorate compounds. Imagine microscopic shards of glass mixed with rust and toxic chemicals, and you're getting close. The Viking landers in 1976 first detected perchlorates in Martian soil. Later missions confirmed their widespread presence at concentrations of about 0.5 to 1% by weight. Perchlorates are toxic to humans, damaging the thyroid gland and disrupting hormones even at low exposure levels. They're also highly reactive oxidizers used in rocket fuel and explosives. Every grain of Martian dust carries these chemicals. When astronauts return from the Moon, they describe lunar dust as one of their biggest challenges. It clings to everything through electrostatic charge, infiltrates equipment, and proved impossible to fully remove from spacesuits. Lunar dust caused significant wear on Apollo mission equipment, scratching helmet visors and degrading seals. And moon dust doesn't even have the chemical reactivity of Martian dust. Mars takes this problem and multiplies it. The planet's thin atmosphere allows dust particles to remain suspended for months during global dust storms. These storms aren't like Earth's sandstorms that last hours or days. Martian dust storms can grow to envelope the entire planet and persist for weeks or months. The 2018 global dust storm that killed Opportunity lasted several months and reduced sunlight reaching the surface by more than 95%. Imagine living in a Mars habitat during a global dust storm. Your solar panels produce almost no power. Your backup systems drain battery reserves. Outside visibility drops to near zero. Communication with Earth continues, but you're alone in the dark, waiting for the skies to clear, hoping your life support holds out. The psychological stress alone could break even the most resilient colonists. But dust creates more insidious problems than blocked sunlight. It accumulates on every exposed surface. Airlocks designed to keep Martian atmosphere out must somehow prevent dust from entering when astronauts return from surface excursions. On the International Space Station, astronauts can't bring dirty clothes or equipment inside without contaminating the pristine environment. On Mars, every surface walk would coat suits in toxic, abrasive dust that must be removed before entering living spaces. The dust contains not just perchlorates but also hexavalent chromium, another toxic compound detected by Curiosity's ChemCam instrument. Breathing even small amounts of hexavalent chromium causes lung damage and cancer. A single airlock failure, one moment of contamination, and colonists breathe poison. Medical facilities on Mars would be minimal at best. There's no emergency room, no specialist surgeons, no advanced diagnostic equipment. A health crisis becomes a death sentence. Then we face the biological effects of Martian gravity itself. At 38% of Earth's pull, Mars exerts enough gravity to keep you on the ground, but not enough to maintain human health over long periods. We know from decades of space station research that microgravity causes bone density loss, muscle atrophy, fluid shifts, vision problems, and immune system dysfunction. But we have virtually no data on the effects of partial gravity between 0 and 1 Earth gravity. The International Space Station provides a microgravity environment, essentially 0G. Astronauts there lose 1 to 2% of bone density per month, despite rigorous exercise regimens. They experience muscle loss even with 2 hours of daily resistance training. After 6 months in orbit, astronauts can barely walk when they return to Earth, requiring weeks or months of rehabilitation to regain normal function. Mars gravity might slow these effects, but we don't know by how much. The only other planetary body humans have visited is the Moon at 16% Earth gravity. Apollo astronauts spent at most 3 days on the lunar surface, far too short to measure long-term health effects. The gap between 16% lunar gravity and 38% Martian gravity might seem small, but biological systems are complex. We literally don't know if human bodies can adapt to Martian gravity for years or decades. Consider pregnant women and children. No human has ever conceived, gestated, or been born in reduced gravity. We have no idea if fetal development would proceed normally in Martian gravity. Would bones develop properly? Would the cardiovascular system adapt correctly? Would brain development occur normally? These aren't abstract scientific questions. They're fundamental to whether humans could actually establish a permanent, multi-generational settlement. Animal studies provide some clues but raise more concerns. Pregnant rats in simulated reduced gravity show developmental abnormalities in offspring. Bone formation in developing animals requires gravitational stress. Muscles need resistance to grow properly. The entire human body evolved over millions of years in 1 Earth gravity. Removing 62% of that force might create physiological problems we can't even predict. Even if adults somehow adapt to Martian gravity, returning to Earth becomes medically dangerous. Astronauts who spend 6 months on the International Space Station require months of rehabilitation. Imagine living on Mars for 5 years, then attempting to return to Earth. Your bones, weakened by years in reduced gravity, must suddenly support more than 2.5 times the weight they've carried for years. Your muscles, atrophied despite exercise, must work against gravity they've never experienced in their adapted state. The cardiovascular system, adjusted to pumping blood in low gravity, must suddenly overcome Earth's pull. The medical consensus suggests that long-term Mars residents might never be able to return to Earth. Their bodies would adapt so thoroughly to Martian conditions that Earth gravity would become intolerable, even dangerous. This isn't science fiction speculation. This is extrapolation from known physiological responses to altered gravity environments. So any Mars colonist must accept a one-way ticket not as romantic adventure, but as medical necessity. You're not just leaving Earth, you'll permanently exile yourself from the planet where human biology evolved to function. Your children, if you have any, would be Martians in every sense, biologically adapted to low gravity and unable to ever visit the world of their ancestors. This raises profound ethical questions. Do we have the right to create a permanent underclass of humans biologically trapped on another planet? What if Mars colonization fails? What if the settlement can't become self-sufficient? Colonists couldn't evacuate back to Earth without risking death from the gravitational transition. They'd be stranded, dependent on supply shipments from Earth for survival, with no escape option. The concept of self-sufficiency itself presents almost impossible challenges. A Mars city would need to manufacture everything from computer chips to medical supplies, grow all its food, recycle all its water and air, repair all its equipment, and maintain all its infrastructure without any help from Earth. Supply shipments from Earth would take 7 months to arrive and could only launch during specific orbital windows every 26 months. If you need a critical spare part and the next launch window is 18 months away, you wait or you die. Agricultural production on Mars faces obstacles that make even optimistic projections seem delusional. Plants need sunlight, water, nutrients, carbon dioxide, and appropriate temperature. Mars provides weak sunlight and abundant carbon dioxide. Everything else must be artificially supplied. Martian regolith contains nutrients, but also those toxic perchlorates. Before planting anything, you'd need to wash the soil to remove perchlorates, requiring water you don't have in abundance. Growing food indoors under artificial lighting requires enormous energy. Studies suggest producing sufficient calories for one person requires roughly 50 to 100 square meters of growing space under optimal conditions. A settlement of 100 people would need 5,000 to 10,000 square meters of pressurized, heated, illuminated greenhouse, a structure requiring millions of kilograms of materials and consuming megawatts of continuous power. Recycling systems for air and water would need to approach 100% efficiency. The International Space Station recycles about 93% of water, meaning 7% is lost and must be resupplied. That's acceptable for a station supplied regularly from Earth. On Mars, that 7% loss rate means your water supply slowly evaporates into nothing unless you can extract replacement water from Martian ice, again requiring energy you barely have. Air recycling faces similar constraints. The ISS uses chemical scrubbers and electrolysis to maintain breathable atmosphere, but these systems require regular replacement parts and consumables. Some components wear out and can't be recycled. A Mars settlement would need to manufacture replacement filters, scrubber materials, and mechanical parts from Martian resources. This requires mining, refining, chemical processing, and precision manufacturing, each step demanding specialized equipment, expertise, and energy. Let's examine the mining and manufacturing challenge more closely, because this is where the dream of Martian self-sufficiency collides headfirst with thermodynamic reality. On Earth, we have the luxury of billions of years of geological processes that concentrated useful ores into deposits we can exploit. We have liquid water for processing. We have dense atmosphere for industrial processes. We have abundant energy from fossil fuels, hydroelectric dams, and nuclear plants. We have millions of skilled workers and centuries of accumulated industrial knowledge. Mars has rocks, just rocks. The planet lacks plate tectonics, the geological recycling process that on Earth creates concentrated ore deposits through subduction, volcanism, and hydrothermal activity. Mars's crust is relatively uniform in composition. Finding concentrated deposits of useful metals would be extraordinarily difficult. You might need to process tons of regolith to extract kilograms of iron, copper, or aluminum. Processing ore requires heat, intense heat. Smelting iron requires temperatures around 1,500 degrees Celsius. Aluminum production needs around 2,000 degrees Celsius and enormous electrical power for electrolysis. On Earth, we use massive electric arc furnaces consuming megawatts. Where does a Mars settlement get this energy? Solar panels covered in dust? Nuclear reactors we haven't yet launched? The energy budget simply doesn't close. Even if you somehow generate sufficient power and extract raw metals, you then need to manufacture components. Computer chips require ultra-pure silicon processed in cleanroom environments with precision measured in nanometers. Medical equipment needs sterile manufacturing facilities. Pressure suits require specialized fabrics and seals. Each product demands specific materials, tools, expertise, and quality control. The supply chain complexity of modern technology is staggering. Consider something as simple as a replacement seal for an airlock. On Earth, this might be a standardized rubber O-ring costing a few dollars. On Mars, you'd need to synthesize rubber from Martian resources, requiring chemical processing equipment, or manufacture it from alternative materials with appropriate flexibility and durability at extreme temperatures. The engineering knowledge, equipment, and materials for one simple seal represents months or years of infrastructure development. Now multiply that problem across thousands of components. Every valve, wire, computer chip, solar panel, battery, motor, pump, sensor, and structural element requires its own manufacturing process, materials, and expertise. Earth's industrial civilization took centuries to develop this capability, building on previous generations' knowledge with billions of people contributing. A Mars settlement of even thousands of people would struggle to replicate even a fraction of this capability. The psychological and social challenges deserve equal attention. Humans evolved in Earth's environment, not just the gravity and atmosphere, but the sensory richness. We evolved under blue skies with wind on our faces, rain on our skin, the smell of Earth after storms, the sound of rustling leaves and bird songs, the sight of greenery and flowing water. These aren't luxuries, they're the environmental inputs our brains expect and need for mental health. Astronauts on the International Space Station report profound emotional responses to viewing Earth from space, the overview effect that puts human conflicts in cosmic perspective. But they're only away for months and can see Earth constantly, a beautiful blue marble reminding them of home. Mars colonists would see a distant star where Earth orbits, indistinguishable from other bright points of light. The psychological isolation would be absolute. Antarctica research stations provide our best analog for isolation, confinement, and harsh environment. Winter overcrews at McMurdo Station and South Pole Station experience significant psychological stress, despite knowing rescue is theoretically possible, and their mission has a definite end date. Mars colonists would know rescue is impossible, and their mission never ends. They live in artificial habitats or die. There's no going outside for fresh air, no emergency evacuation, no end to confinement. Studies of Antarctic winter overcrews document increased depression, anxiety, interpersonal conflict, and cognitive decline during the dark winter months. These are highly screened, trained individuals who volunteered knowing the challenges. Now imagine that stress level sustained not for months, but for years or decades in an environment far more hostile than Antarctica, with no possibility of leaving. The psychological breaking point wouldn't be a question of if, but when. Social dynamics in small, isolated groups tend toward dysfunction over time. Interpersonal conflicts that would be minor annoyances on Earth become unbearable when you can't escape the person who irritates you. You eat with them, work with them, breathe recycled air that passed through their lungs. Privacy becomes impossible in cramped quarters. Sexual tensions, romantic entanglements, and social hierarchies would create drama that on Mars could turn lethal if cooperation breaks down. Earth history shows that isolated settlements often fail. Early European colonies in the Americas saw mortality rates of 50 to 90% in the first years. Roanoke Colony vanished entirely. Jamestown survived only through supply shipments and reinforcements from England. These settlements had breathable air, liquid water, edible plants and animals, and supply ships arriving every few months across an ocean. Mars settlements would have none of these advantages. The communication delay alone creates governance nightmares. Radio signals between Earth and Mars take anywhere from 3 to 22 minutes one way, depending on planetary positions. A simple conversation becomes impossible. Every question requires 6 to 44 minutes for a round-trip answer. Emergency situations demanding immediate expertise from Earth specialists would unfold in real time, while colonists wait agonizing minutes for responses. This delay means Mars settlements must be essentially autonomous in decision-making. But autonomous from whom? If corporations fund the settlement, do they own it? Do colonists have rights? Can they be ordered to take dangerous actions against their will? If governments establish the settlement, which laws apply? Can colonists be prosecuted for crimes on Mars? Who enforces laws when police are millions of miles away? The legal and ethical framework for Mars settlement remains essentially undefined. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but says nothing about private ownership or corporate claims. If a company invests billions in Mars infrastructure, can they claim ownership of land, resources, or even the colonists' labor? Space law experts argue about these questions without consensus. Then we confront the ultimate question. Why? Why attempt something so difficult, expensive, dangerous, and uncertain? The usual arguments fall apart under scrutiny. Scientific research? We can learn far more with robotic missions costing a fraction of human missions. Backing up human civilization? Mars is harder to live on than the most extreme Earth environment after any plausible catastrophe. Mining resources, the cost of returning anything from Mars to Earth makes terrestrial mining look absurdly cheap by comparison. The romantic notion of humanity becoming a multi-planet species sounds inspiring until you examine the practicalities. We're not becoming a multi-planet species by establishing a tiny outpost of people barely surviving in artificial habitats, completely dependent on Earth support, unable to reproduce sustainably, and trapped by their own biology. That's not a new branch of humanity. It's a remote research station with delusions of grandeur. Some argue that pushing technological boundaries justifies the effort, that attempting Mars colonization would drive innovation benefiting Earth. This argument might hold if the technologies developed were applicable to Earth problems, but engineering solutions for Martian dust, near-vacuum atmosphere, and cosmic radiation don't translate to solving climate change, poverty, or disease on Earth. The technologies are too specialized, too expensive, and too divorced from terrestrial needs. The financial cost deserves serious consideration. Estimates for establishing even a small Mars settlement run from hundreds of billions to trillions of dollars. NASA's current budget is roughly $25 billion annually. The entire global space industry generates perhaps $500 billion per year. A Mars settlement would consume a substantial fraction of global space resources for decades while producing essentially zero economic return. Compare that investment to what the same money could accomplish on Earth. Trillions of dollars could revolutionize renewable energy, eliminate extreme poverty, cure diseases, restore ecosystems, or fund education for billions of people. The opportunity cost of Mars colonization is measured in human lives that could be saved or improved with the same resources applied to terrestrial problems. Now let's examine one of the most deceptive aspects of Mars colonization proposals, the timeline. Visionaries promise settlements within decades, but the engineering reality suggests something far different. Consider what we've actually accomplished in space exploration. Humans first reached the Moon in 1969, 57 years ago as of 2026. In all that time, only 12 people have walked on the lunar surface, and we haven't returned since 1972. The Moon is 3 days away, Mars is 7 months away. The International Space Station, humanity's most ambitious space project currently operational, took 13 years and over $100 billion to construct with contributions from 15 nations. It supports a crew of 6 to 7 in low Earth orbit, protected partially by Earth's magnetosphere, easily resupplied, and quickly evacuated in emergencies. The ISS has required constant maintenance, multiple emergency repairs, and continues to experience equipment failures despite being the most sophisticated spacecraft ever built. Now imagine constructing something 1,000 times more complex on Mars. Not just a station, but a complete city infrastructure, habitats, greenhouses, manufacturing facilities, power plants, mining operations, hospitals, laboratories, communication arrays, landing pads, fuel production plants, and all the interconnecting life support systems. The construction timeline alone would span decades, requiring hundreds of cargo missions and continuous astronaut presence for assembly and maintenance. Each cargo mission during favorable launch windows, which occur every 26 months, can deliver perhaps several tons of payload to Mars' surface with current technology. SpaceX's Starship promises 100 tons to Mars' surface, but that's an optimistic projection for a vehicle that hasn't yet successfully completed a full mission profile. Even accepting that optimistic number, building a city would require hundreds of Starship flights delivering tens of thousands of tons of equipment, materials, and supplies. The logistics become absurd when you calculate the numbers. A small settlement supporting 100 people might require 5,000 tons of initial infrastructure, habitats, power systems, life support, tools, equipment, supplies, and redundant backups. At 100 tons per flight, that's 50 cargo missions before a single human arrives. At current launch costs of perhaps $100 million to $200 million per mission, and that's optimistic, you're spending $5 to $10 billion just on cargo delivery before anyone lives there. But wait, there's more. Those cargo missions must land successfully. Mars landing has roughly a 50% historical success rate. Of 49 Mars missions attempted through 2025, only about half succeeded. We've gotten better with recent missions, but Mars continues destroying spacecraft. The entry, descent, and landing phase, the 7 minutes of terror, remains extraordinarily difficult. You're hitting atmosphere at 20,000 kilometers per hour, decelerating through thinner-than-Earth air, and landing precisely despite dust storms and rough terrain. Every failed cargo mission doesn't just cost money, it potentially costs lives. If the mission carrying water recycling equipment crashes, colonists might die of thirst, waiting 2 years for a replacement. If the power generation modules fail to land, there's no electricity. If medical supplies are lost, injuries become fatal. The entire settlement exists on a knife's edge, where single failures cascade into catastrophe. Then consider the human missions. Current Mars mission profiles suggest crews of 4 to 6 for initial landings. These astronauts would need to survive 7 months of deep space radiation during transit, land successfully, establish initial base operations, and survive until the next crew arrives 26 months later. If anything goes catastrophically wrong during those first months, they're dead. There's no rescue mission. Earth is too far away, the planetary positions are wrong, and no spacecraft exists that could reach them in time. The psychological pressure of being the first Mars astronauts would be immense. You'd know the entire world watches your every move, transmitted with minutes of delay. You'd know that millions of people invested their hopes in your success. You'd know that failure means not just your death, but potentially the end of Mars exploration for generations. And you'd know that every decision you make could be your last, because unlike test pilots who accept risk for themselves, your failure dooms your crewmates too. The selection criteria for Mars astronauts would need to be impossibly strict. You'd need people with exceptional physical health, psychological resilience, technical expertise across multiple disciplines, ability to work in confined spaces with the same small group for years, willingness to never return to Earth, and acceptance of probable early death from radiation-induced cancer. Oh, and they should probably be young enough to survive the journey, but experienced enough to handle emergencies, sterile or willing to never have children naturally, and free from any genetic predisposition to radiation-sensitive cancers. Finding even a dozen people who meet all these criteria would challenge any selection program. Now imagine recruiting hundreds or thousands for a growing settlement. The volunteer pool shrinks dramatically when you're honest about the risks, the hardships, and the permanence of the decision. Mars colonization isn't a camping trip or a tour of duty. It's voluntary exile to a toxic wasteland where you'll probably die young from cancer or equipment failure. Some proponents argue that we'll develop better technology before attempting full colonization, solving many of these problems. This argument assumes linear technological progress, but history shows that's not how breakthrough technologies emerge. We haven't developed significantly better radiation shielding in 60 years of space exploration. We haven't solved the bone density loss problem despite decades of research. We haven't created closed-loop life support systems that work indefinitely without resupply. The technologies needed for Mars colonization aren't just incrementally better versions of what we have, they're qualitatively different. We'd need something like science fiction force fields to deflect radiation, or genetic engineering to make humans radiation resistant, or artificial gravity generation to prevent bone loss, or molecular assemblers to manufacture complex equipment from raw materials. These aren't engineering problems, they're physics problems that might not have solutions compatible with known physical laws. Even the most optimistic technology projections run into fundamental barriers. Energy, for instance, is governed by thermodynamics. You can't extract more energy from sunlight than the sun provides. You can't create matter from nothing. You can't violate conservation of mass and energy. Mars receives less solar energy than Earth, period. Any technology operating on Mars must work within that constraint. Wishing for better solar panels doesn't change the amount of sunlight available. The same applies to radiation. High-energy particles carry momentum and energy determined by their velocity and mass. Stopping them requires absorbing that energy into shielding material. There's no magic material that deflects cosmic rays without being massive. Physics doesn't care about our engineering ambitions. The universe operates according to mathematical laws that remain indifferent to human desires for cosmic expansion. Biological limits are equally inflexible. Human cells evolved to repair certain levels of radiation damage. Exceed those levels consistently, and repair mechanisms fail. We can't simply decide to evolve radiation resistance. Evolution operates on timescales of millions of years, through selection pressure. We could potentially use genetic engineering, but that raises profound ethical questions and technical challenges we're nowhere near solving. Consider the hubris required to believe we can casually, genetically engineer humans to survive on Mars. We barely understand the full complexity of human genetics. The human genome contains roughly 3 billion base pairs encoding 20,000 genes with complex regulatory networks. Most genes have multiple functions. Changing one thing often breaks something else. We've cured some single gene disorders, but creating radiation-resistant humans would require modifying multiple systems: DNA repair, cancer suppression, immune function, and cellular metabolism. Even if we developed such modifications, who gets to decide what changes are acceptable? Do we create a separate species of radiation-resistant humans who can never return to Earth? Do their children inherit these modifications, creating a permanent genetic divergence? At what point do Martian-adapted humans stop being human in any meaningful biological sense? These aren't hypothetical ethics questions, they're fundamental issues any serious Mars colonization effort must confront. Let's shift our perspective outward for a moment and consider Mars in the broader context of cosmic habitability. Our solar system contains 8 planets, dozens of moons, and countless smaller bodies. Of all these worlds, only Earth supports life as we know it. This isn't coincidence, it's the result of an extraordinarily specific set of conditions that came together through billions of years of cosmic accidents. Earth orbits in the Sun's habitable zone, where temperatures allow liquid water. Our planet has sufficient mass to retain atmosphere, but not so much that we became a gas giant. We have a large moon, probably created when a Mars-sized object struck proto-Earth 4.5 billion years ago, that stabilizes our axial tilt, preventing extreme climate variations. We have plate tectonics recycling carbon and maintaining atmospheric balance. We have a magnetic field protecting us from radiation. We have a Jupiter-mass planet in the outer solar system, deflecting many asteroid impacts that might otherwise sterilize Earth. Every one of these factors was necessary for complex life to emerge and thrive. Remove any single element, the Moon, the magnetic field, plate tectonics, Jupiter's gravitational influence, and Earth might be as lifeless as Mars. We exist because of cosmic luck, not because life naturally emerges on rocky planets. The universe isn't designed for life. Life desperately clings to the rare places where conditions permit survival. Mars lacks nearly all of Earth's life-enabling features. It's smaller, so it cooled faster and lost its magnetic field billions of years ago. This allowed solar wind to strip away most of its atmosphere. Lower gravity meant it couldn't retain lighter elements like hydrogen. No plate tectonics meant no carbon recycling. Distance from the Sun meant less energy. Mars is dead not through some temporary setback, but through fundamental planetary physics that operated over billions of years. Understanding this deep history reveals why terraforming Mars, transforming it into an Earth-like world, isn't just difficult, but likely impossible with any technology we can imagine. Proposals to terraform Mars typically suggest releasing frozen carbon dioxide from polar caps to thicken the atmosphere, creating greenhouse warming to melt water ice, and possibly importing volatiles from asteroids or comets. These ideas sound plausible until you examine the scale and timeline. Even if you released all the carbon dioxide in Mars's polar caps and regolith, and measurements from the Mars atmosphere and volatile evolution mission in 2015 suggest there's less than we thought, you might achieve atmospheric pressure of perhaps 20 to 40 millibars. That's still just 2 to 4% of Earth's pressure. You'd need nitrogen, oxygen, and water vapor to create a breathable atmosphere. Mars doesn't have enough of these volatiles. Importing them from elsewhere in the solar system would require moving billions of tons of material across interplanetary distances. The energy requirements are astronomical in the literal sense. Redirecting even small comets or asteroids to Mars' impact trajectories would require propulsion systems far beyond our current capabilities. And you'd need to do this thousands of times over centuries or millennia. The total energy investment would exceed all the energy humanity has produced in our entire history. Even if you somehow created a thicker atmosphere, Mars's low gravity means it would slowly escape to space over millennia, the same process that created current conditions. Without a magnetic field, solar wind would continue stripping the atmosphere. You'd need to constantly replenish it, an ongoing investment of resources and energy continuing indefinitely. You're not building a garden, you're fighting entropy forever. Some propose creating an artificial magnetic field to protect a theoretical Martian atmosphere. This would require generating a dipole field comparable to Earth's, which involves moving massive amounts of electric charge or using superconducting magnets larger than anything we've ever built. A 2017 study suggested placing a magnetic dipole shield at the Mars-Sun L1 Lagrange point, the gravitationally balanced point between Mars and the Sun. This shield would need to generate a magnetic field of 1 or 2 Teslas over a cross-section comparable to Mars's size. The engineering challenges are staggering. The largest superconducting magnets on Earth, like those in the Large Hadron Collider, generate fields of 8 Teslas, but only over tiny volumes. Scaling to Mars-size protection would require millions of tons of superconducting material maintained at cryogenic temperatures using enormous power inputs. The structure would need to maintain precise position at the L1 point, requiring continuous thrust against solar pressure and gravitational perturbations. The concept is theoretically possible but practically absurd with foreseeable technology. All of this assumes we should terraform Mars, which raises profound ethical questions. Mars might contain extinct life or even dormant microbes in subsurface ice. Discovery of Martian life, even microbial, would be the most significant scientific finding in human history. It would prove life emerges wherever conditions permit, suggesting the universe might teem with life. It would provide a second example of biology, allowing us to determine what features are universal to life and what features are Earth-specific accidents. But if we terraform Mars before thoroughly searching for indigenous life, we'd contaminate the planet irreversibly. Earth microbes already contaminate our spacecraft despite rigorous sterilization. Microbes hitching rides to Mars would find niches where they could survive, potentially outcompeting or destroying native Martian ecosystems before we even discover them. We'd erase an irreplaceable scientific archive and possibly commit xenocide, the destruction of an alien biosphere, out of impatience and arrogance. The scientific case for robotic exploration rather than human colonization becomes overwhelming when you consider what we can learn. The Perseverance rover and Ingenuity helicopter have revolutionized Martian science since landing in February 2021. Perseverance drills rock cores, analyzes chemical compositions, and caches samples for potential future return to Earth. Ingenuity demonstrated powered flight in Mars's thin atmosphere, completing dozens of flights far exceeding its initial 5-flight mission. These robots cost roughly $2.7 billion total, less than a single human mission would cost, and operate for years without life support, radiation shielding, or return fuel. They don't get lonely, don't need food or water, don't suffer radiation damage the way humans do, and can be left permanently on Mars without ethical concerns. The scientific return per dollar invested is orders of magnitude higher than human missions would provide. Future robotic missions could be even more capable. Artificial intelligence improvements will enable more autonomous decision-making, reducing the communication delay handicap. Better instruments will detect chemical signatures of life with greater sensitivity. Sample return missions could bring Martian rocks and soil to Earth for detailed laboratory analysis impossible on Mars. We could explore lava tubes, polar caps, and deep subsurface environments too dangerous for human explorers. The Martian moon Phobos presents particularly interesting opportunities. It orbits only 6,000 kilometers above Mars' surface, closer than any major moon orbits its planet in the solar system. Phobos might contain water ice and certainly contains Martian material ejected by ancient impacts. A robotic sample return mission to Phobos would be far easier than landing on Mars' surface, yet would provide Martian material for study. We could learn nearly everything we want to know about Mars without risking human lives. But here's the deeper question that cuts to the heart of this entire discussion. What drives the obsession with Mars colonization, if not science? I think it's fundamentally about meaning and narrative. Humans are storytelling creatures. We need grand narratives that give purpose to our existence. For centuries, that narrative was exploration and expansion, crossing oceans, claiming continents, pushing frontiers. The American myth of the frontier is particularly powerful in shaping Mars colonization rhetoric. The idea that civilization advances by pushing into wilderness, that challenges build character, that manifests destiny, drives humanity outward. These narratives dominate American cultural identity. Mars becomes the new world, early colonists become pioneers, and we reenact the expansion westward that defined American history. But this narrative conveniently forgets the human cost of frontier expansion on Earth. The American westward movement involved genocide of indigenous peoples, environmental destruction, brutal working conditions, and mortality rates that would be unacceptable today. The romantic image of pioneers building civilization from wilderness erases the suffering, failure, and death that characterized frontier life. Most frontier settlements failed. Most pioneers lived hard, short lives in difficult conditions. Mars colonization rhetoric borrows this mythology without acknowledging its dark realities. We imagine brave pioneers building a new world, but we don't imagine the cholera outbreaks, the starvation winters, the conflicts over scarce resources, the exploitation of desperate people by those controlling supply lines. We imagine the successful settlement, not the 90% who died trying or the indigenous Martian environment we destroy in the process. The parallel gets worse when you consider that Earth's frontier expansion was motivated largely by resource extraction and economic exploitation. The Spanish sought gold, the British sought agricultural land and resources. The American West was settled for farmland, minerals, and timber. These ventures made economic sense, however brutal their methods, because the resources extracted had value exceeding the costs of extraction. Mars has no such economic case. There's no resource on Mars valuable enough to justify the cost of extraction and return to Earth. Water exists more accessibly on asteroids. Metals are cheaper to mine on Earth. Even if Mars contained pure platinum lying on the surface, the energy cost of returning it to Earth would exceed its market value. Mars colonization can't be funded by resource extraction because the economics are impossible. Some argue that Mars colonization is about human survival, backing up the species against existential threats to Earth. This argument sounds compelling until you enumerate what could threaten Earth badly enough that Mars becomes the preferable option. Nuclear war? The worst nuclear winter scenario still leaves Earth more habitable than Mars. Climate change? Even a runaway greenhouse effect wouldn't make Earth as hostile as Mars. Asteroid impact? The impact that killed the dinosaurs left Earth far more livable than Mars. Essentially, any catastrophe that makes Earth less habitable than Mars would need to eliminate the atmosphere, boil away the oceans, destroy the magnetic field, and sterilize the surface through radiation. At that point, we're talking about planetary destruction on a scale that wouldn't leave survivors anywhere. If Earth becomes uninhabitable, a Mars colony dependent on Earth supply chains dies shortly thereafter. The logic gets circular. We need Mars colony to survive Earth's destruction, but Mars colony can't survive without Earth support, so Mars colony doesn't actually protect against Earth's destruction. A true backup of humanity would need to be completely self-sufficient, which, as we've discussed, is impossibly difficult given current and foreseeable technology. You can't back up humanity with a settlement that relies on the original for survival. A far more practical approach to species survival would be hardened facilities on Earth designed to survive catastrophes. Deep underground complexes with stored resources, genetic material, knowledge archives, and manufacturing capability could preserve humanity and restart civilization after nearly any plausible disaster. The cost would be a tiny fraction of Mars colonization, and the facilities would be vastly more survivable since they'd benefit from Earth's atmosphere, gravity, and existing resources. Or consider building space habitats in Earth orbit or at Lagrange points. These could be designed with radiation shielding, artificial gravity through rotation, and immediate access to Earth's resources while remaining separate from surface catastrophes. The O'Neill cylinder concept, proposed in 1974, could house thousands in rotating habitats that simulate Earth gravity while being far easier to supply than Mars surface settlements. You get the benefits of space settlement without the disadvantages of planetary surface confinement. The Moon presents a more sensible intermediate target than Mars for any expansion beyond Earth. It's 3 days away instead of 7 months. Communication has only a 3-second round-trip delay instead of up to 44 minutes. Emergency evacuation is possible. Supply missions are vastly cheaper and more frequent. The Moon has water ice in permanently shadowed craters, useful metals in the regolith, and solar power availability. Lunar gravity is lower than Mars, 16% versus 38%, which might be worse for human health but is better for launching resources to orbit. A lunar settlement could supply raw materials for space construction far more easily than Earth or Mars. Helium-3, rare on Earth but present in lunar regolith, could theoretically fuel fusion reactors if we ever develop practical fusion power. The Moon's far side offers radio silence shielded from Earth's electromagnetic noise, ideal for radio astronomy. None of these advantages make lunar settlement easy, but they make it vastly more practical than Mars. If we're serious about expanding humanity beyond Earth, we should master living on the Moon before attempting Mars. If we can't create a self-sufficient settlement on the Moon with all its proximity advantages, we have no business attempting Mars. The Moon serves as a proving ground where failure means difficult rescue rather than certain death. Yet Mars captures the imagination in ways the Moon doesn't. Why? Partly because we've been there. The Moon feels conquered, explored, done. Mars remains mysterious, unexplored, frontier. But mostly because Mars offers the illusion of being Earth-like. It has a day nearly identical to Earth's 24 hours. It has polar ice caps and seasons. It has clouds and weather. It has red soil that looks like desert landscapes. We can imagine walking on Mars in ways harder to imagine on the airless, dusty Moon. This psychological appeal makes Mars dangerous as a policy objective. We pour resources into Mars missions because it feels like somewhere we could live, ignoring the reality that it's nearly as hostile as the vacuum of space. The illusion of familiarity seduces us into underestimating the challenges. It's like assuming you can survive Antarctica because you've been camping in winter. You're dead before you understand the difference in scale. The commercial space companies promoting Mars colonization, particularly SpaceX, benefit from this psychological appeal. Elon Musk's stated goal of making humanity multiplanetary resonates emotionally even when the practical details don't withstand scrutiny. Marketing. Mars as humanity's backup planet, as the frontier for a new generation, as the answer to meaning in a secular age. These narratives drive public enthusiasm and investment regardless of feasibility. And let's be clear, SpaceX has accomplished remarkable things. Reusable rockets were considered impractical until Falcon 9 demonstrated routine booster recovery and reuse. The cost of launching cargo to orbit has dropped significantly. Starship promises even cheaper access to space if it achieves its design goals. These are genuine engineering achievements deserving recognition. But engineering achievements in rocket technology don't automatically translate to successful Mars colonization any more than inventing better ships guaranteed successful Arctic exploration. Many Arctic expeditions had the best ships available and still ended with entire crews dead from scurvy, starvation, and cold. Technology is necessary but not sufficient for success in extreme environments. You also need a practical plan, realistic assessment of challenges, and, crucially, a compelling reason to go that justifies the inevitable deaths. The 19th century Arctic expeditions at least had practical goals: finding the Northwest Passage for trade routes, reaching the North Pole for national prestige, mapping unknown regions for scientific knowledge. These goals justified the risks to the people who accepted them. What justifies Mars colonization deaths? Not science, robots do that better. Not resources, economics don't work. Not species backup, dependency on Earth negates that. Not expansion, there's nowhere to expand to from Mars. We're left with intangibles, inspiration, adventure, the human spirit of exploration. These matter, I don't dismiss them, but are they worth lives? Are they worth trillions of dollars? More importantly, whose lives and whose dollars? The people funding Mars missions aren't the ones going. The engineers designing spacecraft return home to families. The astronauts accepting the risks are self-selected risk-takers, but they're making decisions affecting others, families who lose them, future colonists depending on their success, humanity's reputation in the cosmos. There's an uncomfortable elitism embedded in Mars colonization discourse that deserves examination. The people most enthusiastically promoting Mars settlement tend to be wealthy technologists, aerospace engineers, and science fiction enthusiasts, predominantly from developed nations, predominantly male, predominantly with the resources to imagine themselves or their children as potential colonists. This isn't the demographic most affected by Earth's actual problems. While billionaires fantasize about Mars cities, billions of people on Earth lack clean water, adequate nutrition, basic healthcare, and education. The disconnect is morally staggering. We're proposing to spend trillions making a dead planet marginally habitable for a few thousand people, while failing to make Earth fully habitable for the 8 billion already here. The opportunity cost isn't abstract. It's measured in preventable deaths, treatable diseases left untreated, and solvable problems left unsolved. Imagine presenting the choice to someone in a developing nation struggling with poverty. We can spend $1 trillion bringing clean water, sanitation, healthcare, and education to your community, lifting millions out of poverty and saving countless lives. Or we can spend that $1 trillion sending 100 people to live in tubes on Mars where they'll probably die of radiation cancer. Which do you choose? The answer is obvious to anyone not intoxicated by techno-utopianism. The argument that we can do both rings hollow when we're demonstrably not doing both. Global spending on space exploration runs about $90 billion annually. Global spending on foreign aid is roughly $200 billion. Meanwhile, estimates suggest that ending extreme poverty worldwide would cost approximately $175 billion annually for 20 years. We could solve poverty with money currently spent on far less pressing priorities, yet we don't. Adding Mars colonization to the budget doesn't somehow unlock additional resources for Earth's problems. It diverts resources from them. Some counter that space technology creates spin-offs benefiting Earth. This is partially true. Satellite technology enables GPS, weather forecasting, communications, and Earth observation. Medical devices, water purification systems, and materials science have benefited from space research. But these spin-offs came primarily from Earth orbit activities and robotic missions, not human space exploration. The return on investment is higher for targeted research than for expensive human missions. Moreover, any technology developable through space research could be developed more efficiently through direct research on Earth. If we want better water purification, we should fund water purification research directly rather than hoping it emerges as a spin-off from Mars life support systems. If we want advanced materials, we should fund materials science, not wait for Mars habitat construction to drive innovation. The spin-off argument is essentially saying we'll develop useful technology by accident while doing something impractical, which is a terrible research strategy. The environmental cost of space launches deserves consideration too. Rocket launches emit significant pollutants, carbon dioxide, black carbon, water vapor in the stratosphere, and various combustion products. A single Falcon 9 launch emits roughly 425 tons of carbon dioxide. Starship, being far larger, would emit vastly more. A Mars colonization program requiring hundreds or thousands of launches would contribute measurably to climate change and ozone depletion. SpaceX argues that Starship will eventually use methane synthesized from atmospheric carbon dioxide and water, making it theoretically carbon neutral. But this requires enormous energy inputs to synthesize fuel, and that energy must come from somewhere. If it comes from fossil fuels, you're just moving the emissions around. If it comes from renewables, you're using clean energy for rockets that could instead replace fossil fuels for ground transportation or industry. Either way, the climate cost is real. There's bitter irony in using resources to escape a planet we're making less habitable through our own actions. Mars colonization is presented as insurance against making Earth unlivable, but the resources spent on Mars could instead prevent making Earth unlivable in the first place. We're building lifeboats while drilling holes in the ship, when we could instead patch the holes and stay aboard the perfectly good vessel we already have. Climate change is the existential threat our civilization actually faces, not in centuries or millennia, but in decades. Rising temperatures, extreme weather, sea level rise, ecosystem collapse, agricultural disruption, and climate refugees will reshape human civilization within our lifetimes. This is the emergency demanding our attention and resources. Next to climate change, Mars colonization is a hobby for the wealthy, a distraction from problems we could actually solve. The comparison becomes even starker when you consider that the technology needed to survive on Mars, closed-loop life support, renewable energy systems, efficient food production in controlled environments, recycling systems, is exactly the technology we need to make Earth sustainable. If we developed these systems for Earth implementation instead of Mars application, we'd solve real problems affecting real people now rather than hypothetical problems affecting hypothetical future Mars colonists. Vertical farming, for instance, could revolutionize food production in urban areas and regions affected by climate change. The technology exists but needs refinement and scaling. Investment in perfecting vertical farming would provide food security for billions while reducing agriculture's environmental footprint. The same technology could theoretically grow food on Mars, but why not use it where 8 billion people already live? Water recycling technology could address water scarcity affecting 2 billion people. Renewable energy systems could power the developing world without carbon emissions. Advanced materials could make infrastructure more resilient to extreme weather. Carbon capture could slow climate change. These aren't science fiction technologies we need to invent. They exist, but need investment to scale and deploy. Every dollar spent on Mars is a dollar not spent making Earth better. The psychological framing of Mars colonization as Plan B is particularly insidious because it implies we can abandon Earth if we mess it up badly enough. This creates moral hazard reduced incentive to protect Earth if we believe we have an alternative. But as we've established, Mars isn't a viable alternative for civilization. It's not even a viable alternative for a tiny subset of humanity. The idea that we can escape consequences of our planetary mismanagement by moving to a worse planet is fantasy enabling continued mismanagement. We have exactly one planet capable of supporting human civilization: Earth. We evolved here over millions of years. Our biology is optimized for these conditions. Our atmosphere, gravity, temperature range, water cycle, and ecosystems provide everything we need. This planet is precious beyond measure, irreplaceable, and currently the only known harbor for life in the cosmos. Treating it as disposable because we imagine Mars as a backup is like burning down your house because you think you can camp in the desert. The truly inspiring vision isn't escaping to Mars, it's fixing Earth. Imagine if we applied the ambition, creativity, engineering excellence, and resources currently aimed at Mars toward making Earth genuinely sustainable. Imagine cities powered entirely by renewables, transportation systems that don't emit greenhouse gases, agriculture that works with ecosystems rather than destroying them, economies that don't require endless growth on a finite planet. This is technically achievable. We know how to generate clean energy. We know how to design efficient buildings. We know how to protect ecosystems while meeting human needs. We know how to create circular economies that recycle materials rather than depleting resources. What we lack isn't technology but political will, cultural change, and economic restructuring. These are hard problems, perhaps harder than technical challenges, but they're solvable if we prioritize them. The same innovative spirit that imagines Mars cities could reimagine Earth cities as green, efficient, and beautiful. The same engineering that designs Mars habitats could design Earth buildings that generate more energy than they consume. The same resource investment that would fund Mars colonization could fund the largest environmental restoration project in history, bringing back forests, wetlands, and ocean ecosystems. This vision doesn't have the romantic appeal of Mars colonization. Fixing sewage systems, planting forests, and installing solar panels doesn't thrill like rocket launches and planetary settlements. But romance shouldn't dictate civilization-level resource allocation. We're not children choosing the exciting option over the practical one. We're supposed to be mature enough to prioritize actual needs over appealing fantasies.